Okay, so a video solution requested for number 60. This is in chapter 5 of your AP Physics book. A particle starting from rest revolves with a uniformly increasing speed in a clockwise circle in the xy plane. Center of the circle is at the origin. T equals 0, the particle is at x is equal to 0, y is equal to 2. And then after 2 seconds, it's got 1/4 of a revolution. We're trying to determine a number of things here for parts A, B, and C. Let's go ahead and start with a little sketch here. So go ahead and take this over here. Easier for us to do this workout solution at this particular spot. And so let's go ahead and try this. We're going to draw a little sketch based on this situation. So okay, so we have an object that's starting at this particular spot. That's at, let's put some coordinates here. That's at position 0, 2. And then because it's speeding up uniformly along this circle, let's go ahead and just draw a little set of dot diagrams here to show that it's speeding up tangentially. So we would say that it's got some acceleration along the tangent line, and we're going to assume that that acceleration is a constant value, but its direction is constantly changing and so forth. And so we're given that at this particular point in time, it is at 2 meters. Let's move this down here for a second. So it has traveled to this particular spot. It's taken 2 seconds to get there, and we want to determine things like its speed at that point, the average acceleration velocity, the average velocity vector, and the average acceleration vector during that time interval. I'm going to do this just by considering some of our kinematic equations with uniform acceleration. But we're going to consider that instead of using delta x as 1/2 a t squared, just in general, we're going to say that we're going to consider that this is a portion of a circle. We're going to say that the distance that they travel is 1/4 of 2 pi r, and that would be equal to 1/2, and I'm going to say that's the tangential acceleration times t squared. And then let's just go ahead and solve this for a sub t. Okay, so let's see, that would become pi r over 2 is equal to 1/2 a tangential times t squared. Multiply both sides by 2 there, and I get pi r is equal to a tangential times t squared. And then a tangential would just be equal to pi times r all over t squared. In this case, we have some numbers here for us given our initial conditions and our conditions after 2 seconds. We can put that in as a tangential is pi times radius is 2 meters, and that time was 2 seconds for this. And so that would be pi over 2 meters per second squared, and that would be the tangential acceleration. Okay, so that's just the magnitude of it. Its direction is constantly changing. So we're going to say that that is the magnitude of the tangential acceleration. Now, it's asking for what is its speed at 2 seconds. So clearly at that particular point, it's going to be moving straight downward. So its speed would be in the negative y direction. And we can find its magnitude just by using velocity here. Delta v is equal to a tangential times t. And since we have that value for tangential acceleration, that took 2 seconds for us to get there. And so its delta v now would be equal to pi meters per second. And that's how fast it would be moving at that point. And it would be moving straight downward. So its actual velocity there would be equal to, we just call that negative pi j hat meters per second. Okay, and since it's asking for speed, it would just be moving at pi meters per second, and that would be in the downward direction. Let's go ahead and check that really quick with that answer. Yep, so 3.14 meters per second, its speed at that particular point. Now, parts B and C. Let's see, it asks for the average velocity vector during that time. So let's see if we can go ahead and do that. We're going to just go to our definitions of average velocity. So average velocity is generally just delta x over t. Here we're going to say that is delta r, where r again represents sort of like a radial vector instead of a displacement in one dimension. We're going to talk about displacement in 2 dimensions. And so let's go ahead and just write this in unit vector notation. This would be r final minus r initial. These are vectors all over t. And let's see, the final position here after 2 seconds is at a position of 2 I hat plus 0 j hat. So that is its final position. Its initial position, I'm going to subtract away from that the fact that I started up here at 0, 2. So I started at a 0 I hat plus 2 j hat. And then I'm going to divide that by the time, which was 2 seconds. And so with unit vector notation, I see that'd be I hat minus j hat. And that would be in meters per second. Okay, so that would be the average velocity during that time interval. Okay, and then finally, part C is what is the average acceleration? Well, average acceleration, using the same definition, or the same concept, if you will. Average acceleration is change in velocity over time. And so I know its starting velocity was 0 I hat plus 0 j hat. Its velocity after 2 seconds is just negative pi j hat. And so we can go ahead and just solve that for average acceleration to be, let's see, final velocity would be a negative pi j hat, and the initial velocity was 0. And so now I'm just going to go ahead and divide that by 2 seconds. And for that I get negative pi over 2 j hat meters per second squared. Okay, and that would be the average acceleration vector during that time. And sure enough, we wrote that as a negative 1.57 j hat meters per second squared. So there we go. I think the challenge of this question largely was in the first part, determining just how to approach this particular question based on tangential acceleration. Again, we used UAM concepts to just describe the tangential acceleration along that arc, and then we can go through, and then once we get to that point, we use unit vector notation to be able to figure out things like average velocity, average acceleration. There we go, problem number 60, solution for you.